To see the Earth as it truly is, small and blue and beautiful in that eternal silence where it floats, is to see ourselves as riders on the Earth together, brothers on that bright loveliness in the eternal cold, brothers who know now they are truly brothers. Poet Archibald MacLeish gave us the words, an Apollo crew, the pictures. It was the holiday season in December 1968, as astronauts Borman, Lovell, and Anders became the first men to sail beyond the Earth into the aura of another world. The first to sail around that world, our constant moon. The first to look down on its hidden side. The Apollo 8 mission marked the culmination of the first 10 years of NASA's formal existence. A decade of accomplishment in what former NASA Administrator Thomas Paine called man's new domain of life. In 1960, no human being had ever flown above the atmosphere. By 1969, American astronauts had spent almost 6,000 hours in space, had orbited the Earth 959 times, and the Moon 116 times. During the 60s, the 6 suborbital and Earth orbital flights of Mercury proved men could survive in space. The 10 Earth orbital missions of Gemini perfected maneuvering and docking techniques. And the first Apollo missions established forever man's ability to travel beyond the confines of his home planet. In 1969, the historic goal was reached. Apollo 11 accomplished the first manned landing on the moon.
Okay, engine stop. Tranquility Base here. The Eagle has landed.
The first small step of Neil Armstrong.
That's one small step for man, one giant leap for mankind.
Astronaut Armstrong read the dedication plaque on the lunar module as more than 500 million of his fellow human beings watched and listened back on Earth. Then, with astronaut Aldrin, Armstrong began the first-hand exploration of the moon, collected the first of many rock and soil samples, and set up the first of many planned scientific stations. For the richest treasure we seek on the moon is intangible. It is knowledge. Study of the moon and its history may uncover knowledge of our sun, our Earth, our origin, and our destiny. 4 months after our first moon landing, the Apollo 12 mission raised the world's exclusive company of moonwalkers to 4. Behind such headline events, there were thousands of spaceflight equipment tests on the ground, as well as unmanned flight tests. The manned spaceflight program of the 60s was the product of the energies of hundreds of thousands of men and women working directly in the program, in government, universities, and industry. The lunar landing demonstrated that 300,000 people could work closely together to achieve success. They can be credited with pushing forward the very horizons of technical development. Where then, before we preview the future, do we stand now? What can we do that we could not do just a few short years ago? We stand now on the very edge of space, newcomers trying our new skills. We have lived in space and can survive there for at least a few weeks at a time. We can rendezvous and join spaceships together during flight. and we can perform useful work in the new, gradually familiar space environment. We can walk upon the moon, explore its ancient terrain, direct experiments in miniature power stations. We can gather specimens for the clues they give us back in Earth laboratories. Scientific clues revealing facts about the origin and the history of the moon, the Earth, the sun, the solar system. With spaceborne sensors, manned and unmanned, we can see the Earth itself more grandly, can see the forest and the trees, can study rivers, oceans, deserts. We may learn how to prospect on a giant scale for oil, minerals, underground sources of fresh water. We can look down upon the clouds and winds and rains of Earth, are learning how to forecast their formation, perhaps how to alter and control them. We can improve the navigation of our ships and aircraft. We can communicate with the entire world at one time. Presently, we are cooperating in space with many other nations. We shared moon rocks and soil with scientists from all over the world, and we have carried many foreign experiments on our missions. Other countries, in turn, have helped us build and man our worldwide tracking network and have offered contingency recovery assistance to our returning flight crews. With other countries of the world, large and small, we have participated in space treaties, in space science symposiums, in joint launches and satellite missions, in international medical and educational broadcasts using our satellites, and in Earth resource surveys and weather studies. As a nation, the United States will continue to build on the confidence and national security that comes with leadership in space technology and a firm foundation for future world cooperation. President Nixon, in his 1970 policy statement on space, outlined three general purposes: exploring, gaining scientific knowledge, and applying the lessons we learn in space to the early benefit of life on Earth. NASA's programs for the future reflect these purposes. The exploration of the moon is continuing, taking advantage of our hard-won ability to get there and back. Beginning in 1970, landing sites have included the hilly uplands near the crater Fra Mauro and other mountains, rills, and craters believed by scientists to be most rewarding for geological and geophysical studies. In addition to exploring and sampling near the landing sites, an important goal of continuing expeditions to the moon is the establishment of new scientific instrument stations at a variety of sites. These augment the instruments already transmitting from the moon and provide an expanding network for the return of scientific data. Additional stations with seismometers, for example, make possible more complete analyses of the structure of the moon's interior and enable scientists to determine the nature of volcanic and other lunar activity, such as the moonquakes, which have been detected occurring at precise monthly intervals. NASA plans for the final 4 Apollo lunar landing missions in 1971 and 1972 were designed with many new experiments in mind. For example, the use of a lunar drill for penetrating several feet below the surface. To carry equipment and rock samples, this first small cart, called a rickshaw, was developed for Apollo 14 explorers. For extended Apollo missions with longer surface exploration periods, other aids, such as a battery-driven lunar roving vehicle, similar to this prototype, were programmed. The first manned landings on the moon rewarded scientists with a variety of new, exciting data on the age and nature of the moon. But as many questions have been raised as have been answered. Scientists are hopeful that continuing exploration and sample gathering in many different areas of the moon will solve such riddles as, what is the age of the moon and the solar system? Moon rocks gathered in early expeditions ranged in age from 3.5 billion years to 4,600,000,000. What are the huge mass concentrations, under the surface of the moon, massive enough to affect the flight paths of orbiting spacecraft? What is the interior of the moon like? What is the source of the heat that produced the lava filling the moon's flat basins called maria? Why is it that the side of the moon that faces Earth has the smooth basins, while the moon's hidden side is more rugged, mountainous, and pitted? Why have the man-made moonquakes created by impacting space vehicle stages on the moon resounded in such unusually long-lasting waves compared to similar effects on Earth? They resemble those of a bell or of a spoon striking a crystal glass. Why have some familiar plants exposed to lunar material in Earth laboratories shown growth rates 3 or 4 times normal? What is the history of the sun as revealed by the moon's surface? The streams of solar particles that we call sunshine have been falling on the moon for billions of years. The records of this downpour can still be read in the moon's soil and rocks, since there is no wind or rain there to erase them. From the layers and composition of the moon's suntan, we can tell much about the past behavior and chemistry of the sun. What is the possibility of using oxygen and other elements found in moon specimens to support a permanent colony on the moon? These and many more questions, large and small, may be answered as Apollo missions orbiting the moon and landing men on it continue. But the moon is only one target for manned spaceflight investigations in the near future. In November 1972, NASA plans the launch and operation of an experimental manned Earth orbiting laboratory called Skylab, forerunner to permanent space stations. It uses existing Apollo facilities and equipment already proven, paid for, and delivered. A converted Saturn V third-stage tank makes up the orbital laboratory proper, equipped and furnished on the ground as a 2-story mobile home with about as much living and working area as a small 3-bedroom house. Supporting units attached to the laboratory are the airlock containing a central switchboard to manage communications, electric power, and environmental control systems, and the docking adapter, which serves as a berth for visiting spacecraft and contains important experiments. A third unit supports solar telescopes for carrying out one of the major experiments of the program. The complete assembly is placed in near-Earth orbit by the first 2 stages of a Saturn V. A day later, a 3-man crew is launched into orbit by a smaller Saturn 1B. After attaining orbital flight, the crew rendezvous and dock their Apollo spacecraft with the orbiting laboratory. Skylab is designed to provide experience and data on the ability of men to live and work in space for extended periods, in far more spacious quarters than the Apollo spacecraft. Separate crews of 3 men each man the laboratory, the first crew spending about 4 weeks, then returning to Earth, and the next cruise in 1973 remaining in orbit for up to 8 weeks. Short duration flights of men and animals have have revealed certain effects from weightlessness, effects on the circulation of the blood, on red and white blood cells, on ears and eyes, and muscles and bones. In Skylab, over 50% of the experiments on or by the astronauts are biomedical. To learn how to avoid adverse effects on circulation, for instance, is the object of an experiment in which a bellows-like device is applied to the lower body, drawing the blood down much as does normal Earth gravity. The performance of heart and blood vessels will be monitored on board and recorded. Other tests involve daily measurement of weight losses and other physical examinations. In addition to helping men learn how to live in space, Skylab has personal rewards for those of us who remain on the ground. For example, information gained from cardiovascular experiments in a weightless environment may lead to increased comfort and more healthful conditions for long-term bed patients on Earth. Biological tests on mice, human tissues, vinegar flies, and potatoes will add to ground-based research in the life sciences. Substantial benefits to living conditions on Earth are promised from mapping, from surveys of mineral, agricultural, and ocean resources, and from measurements and remedies developed to reduce pollution in the Earth's air and water. The Skylab laboratory can increase our knowledge of the Earth by using cameras and film sensitive to both visible and invisible light waves. As a forerunner to permanent factories in space, Skylab scientists and engineers are able to investigate processes such as electron beam welding and metal joining. We can also experiment with other techniques, taking advantage of previously unavailable space conditions, such as almost total vacuum and zero gravity. Someday it may lead to the growth and fabrication in space of crystals for industrial use and the formation of new materials, processes, and products hitherto unknown. Finally, the laboratory makes possible another milestone in man's search for answers from the stars. Its solar telescopes enable men in space to study the sun unhampered by the distortion and shortwave screening effects of the Earth's lower atmosphere. 230 miles above the gases, dust, and water. Skylab's observatory has several telescope systems for observing, measuring, and recording the sun's radiation, providing man with a more intimate knowledge of this source of energy and life. For use in the latter half of the decade, important spaceflight developments are underway. For instance, to reduce the cost of spaceflight most drastically, a two-stage reusable Space Shuttle is being developed by NASA for launch in the late 70s. Difficult design problems of weight, aerodynamics, and re-entry heating are being overcome. The shuttle will be launched vertically by the rocket engines of its first stage, the booster element. It will reach a speed of several thousand miles per hour, about 40 miles up. The first stage will then peel off and fly back to Earth to land on a conventional aircraft runway. After the first stage has separated, the engines of the shuttle's second stage will be ignited. Streaking through and beyond the thin upper atmosphere, it will accelerate to nearly 18,000 miles per hour to deliver its payload and perform its mission. Later, the second stage and its crew will re-enter. Then land at an airport with its return cargo. The Space Shuttle will be built for up to 100 round-trip flights with minimum maintenance. It will reduce the cost of placing cargo and crew in orbit or returning them to Earth to about 1/10 of what it is now. The planned shuttle will be able to carry payloads of more than 12 tons in men and equipment. This capacity offers new freedom to mission planners in selecting and designing experiments. Scientists will be able to go into space and conduct their own work in a shirt-sleeve environment without first qualifying as astronauts. With the shuttle for transport, technicians will be able to deliver rather than launch unmanned scientific and technical satellites and probes, to place them in widely varying Earth orbits, from equatorial to polar. They can then return to repair, maintain, refuel, and refurbish them, or to reposition or retrieve them and bring them back to Earth. They will be able to place and aim cameras and other sensors, leave them to gather data, then return weeks later to pick up the results. The reusable shuttle may replace 11 different classes of rockets, now used to launch manned and unmanned missions. With its quick launch readiness and maneuvering ability, the reusable shuttle also has a valuable potential as the first space rescue vehicle. Several other space developments are technologically feasible today and seem socially and economically valuable for tomorrow, now that man has begun to live and work in this new domain. For example, NASA is studying designs for an orbiting space station. In one concept, the decks of the orbital station would provide permanent working and living facilities for several men. It could have an operating life of at least 10 years. Living conditions would be comfortable and attractive, with private staterooms, showers, recreation areas, kitchen and dining room, as well as work areas. Such a station would be a self-contained scientific laboratory and research facility, similar to a highly flexible center on Earth, where work can be done in many different scientific and technological areas. Astronomy, physics, chemistry, and the life sciences could benefit. So might research in new materials and manufacturing and other advanced studies to improve the welfare of mankind. The station would be a focal point for productive international cooperation and joint ventures that would include specialists from other countries as members of the team. Some of the other concepts now under study include a reusable nuclear shuttle based on the Nerva nuclear engine, already successfully tested in captive firings, for use between Earth and Moon orbits and for propulsion on interplanetary missions. A versatile space tug for inter-orbit transport and other functions. A very large Earth-orbiting space base, an island satellite for perhaps 100 scientists, technicians, and specialists from almost every occupation. Such a city in space will be a logical outgrowth of the first space stations. As now conceived, it will be a cluster of such stations or sections assembled in space around a central hub or core. By rotating the base or sections, different degrees of gravity will be provided depending on experimental and residential needs. The flow of new data and discoveries from the space base will enrich our knowledge of Earth, its resources, its environment, and the life upon it. In turn, such new knowledge will help improve the quality of life on Earth, the only green and lovely world we know of in the universe. For we are riders on the Earth together, and to understand the mysteries of the universe, we have begun by seeking answers close to home. A challenging course lies ahead. From the manned spaceflight achievements of the 1960s, and that first small step of man upon the moon, July 20th, 1969, We are moving on into the 70s through the increasingly advanced moon exploration missions of 1971 and 1972. To the Skylab missions and Earth orbital experiments of 1972 and 1973. To the Space Shuttle later in the decade. Farther off, there is the space station, the space tug, the space base, the nuclear shuttle, and eventually manned expeditions to the planets. And as in the recent past, we can look forward to discoveries and new knowledge returned as precious cargo from these expeditions into space, bringing new answers for our spaceship Earth and all her passengers.